Raw material is selected, inspected, stored, and prepared for processing. The pusher furnace heats raw steel bars uniformly to high temperatures, ensuring optimal plasticity for subsequent rolling and forming processes. The fully automated pre-rolling stand shapes the heated raw material into preliminary forms. Advanced sensors and controls ensure consistent dimensions, preparing the material efficiently for further processing in the rolling mill. The intermediate rolling line reduces and shapes the pre-rolled material further, enhancing dimensional accuracy before final finishing in later stages. The walking beam cooling bed cools rolled steel uniformly, preventing deformation and ensuring consistent mechanical properties for subsequent processing stages. The hot cutting unit precisely cuts steel to required lengths. Induction hardening in the single bar throughput process rapidly heats individual steel bars using electromagnetic induction, then quenches and tempers them in line to enhance surface hardness, strength, and wear resistance. Material testing ensures the steel meets strict quality standards. The Vickers hardness test uses a diamond indenter to measure surface hardness with high precision. The Brunel method, ideal for softer metals, uses a steel ball to evaluate hardness through indentation. The tensile strength test determines how much load the material can withstand before breaking. Metallographic structure examination analyzes the steel's microstructure to assess grain size, phase distribution, and flaws. In the bright steel plant, steel bars are peeled, straightened, and polished to meet exact dimensional and surface finish requirements. The peeling line 3 removes the outer layer of steel bars to eliminate surface defects and ensure a smooth, clean surface. Following peeling, straightening rollers align the bars precisely to meet strict tolerances for straightness. Roundness measurement then verifies the uniform circularity of the bars to guarantee dimensional accuracy. The testing unit 1 includes several quality control methods. Mix-up inspection prevents material misidentification, ensuring traceability. Eddy current testing with probe systems detects surface and near-surface defects without damaging the material. Phased array ultrasonic testing provides detailed internal flaw detection through advanced imaging techniques. After testing, the bars undergo demagnetization to remove any residual magnetic fields that could affect later processing or applications. Finally, the double peeling system further refines the surface by removing additional layers for exceptional surface quality and precision. In the automotive industry, steel components for the powertrain are manufactured with high precision to ensure strength, durability, and performance under extreme conditions. Rack bars for steering systems are produced to meet exacting standards, providing reliable and smooth steering control. These rack bars are essential parts of steering systems used across various vehicle types, from passenger cars to commercial vehicles. Steel is one of the most essential materials in our modern world, found in everything from vehicles to medical devices to wind turbines. At the heart of its production, especially when recycling scrap metal, lies the electric arc furnace, EAF, a powerful and energy-intensive tool that transforms discarded metal into high-performance steel. In Witten, Germany, the German stainless steel works, Deutsche Edelstahlwerke, stand as a global leader in producing highly alloyed specialty steels. One of their key technologies is the use of massive electric arc furnaces. Each year, the facility processes approximately 500,000 tons of steel scrap, a critical raw material, turning waste into a valuable industrial product. The process begins when steel scrap, collected from various sources, is fed into the EAF. These furnaces are gigantic structures, capable of handling immense quantities of metal. Roughly every 90 minutes, the furnace in Witten is charged and powered up, marking the start of an extraordinary transformation. When electricity is applied to the electrodes, an arc forms. Temperatures inside the furnace quickly soar beyond 1,700 degrees Celsius, over 3,000 degrees Fahrenheit, hot enough to melt even the densest metal. This intense heat allows for a rapid and efficient melting process, significantly reducing the time and energy needed compared to traditional blast furnaces. Once the scrap has melted, the resulting molten steel is tapped from the furnace. This step is highly demanding. Even after the steel has been extracted, the furnace remains blazing hot. The door must be cleaned of glowing slag, a byproduct of the melting process. The conditions are so extreme that machines, not humans, are used to clean the furnace safely. After leaving the furnace, the molten steel is cast into large blocks called billets or slabs. These are still glowing red hot and are immediately transferred to the rolling mill, where they are hardened and shaped. Skilled plant operators guide the heavy steel blocks through pairs of counter-rotating rollers. Despite weighing several tons, the blocks are maneuvered with precision, appearing almost like toys under the control of modern machinery. The final steel products emerging from this process are used in some of the most advanced and demanding industries in the world, including automotive, aerospace, offshore wind energy, and medical technology. The blast furnace is a vital part of iron making, where iron ore is transformed into molten pig iron through a reduction process. At Salzgitter Flachstahl, the blast furnaces are massive, towering over 50 meters, and can produce up to 14,000 tons of hot metal per day. The process begins with the layered charging of raw materials from two bunkers. Iron-bearing materials, like sinter, lump ore, and pellets, coke, and limestone are fed into the top of the furnace via a rotating chute. As these layers descend inside the furnace shaft, they are exposed to rising hot gases produced by blowing preheated air approximately 1,500 degrees C into the bottom through tuyères. The coke combusts in the presence of oxygen, generating carbon monoxide, CO, and heat, approximately 2,000 degrees C. This CO gas rises and reduces the iron oxides in the ore to metallic iron, while the limestone acts as a flux, combining with impurities to form slag. The iron melts and collects at the bottom, forming a pool of molten pig iron, with the less dense slag floating on top. Every 2 hours, the furnace is tapped through a specially drilled tap hole, releasing molten iron, approximately 1,450 degrees C, and slag, which are then separated. Process gas, top gas, rich in CO and carbon dioxide, is captured, cleaned, and partly reused for energy recovery. This efficient and continuous process forms the foundation of steelmaking, as the molten pig iron is transferred to steelmaking converters for further refinement. The steel plant at Salzgitter Flachstahl is one of the core components of the company's integrated steel production. The massive facility spans more than 400 meters in length, large enough to accommodate around 480 single-family homes, underscoring its industrial scale. Molten pig iron, delivered from the blast furnace in torpedo ladles, is transferred into transport ladles, each with a capacity of approximately 200 tons. In the converter hall, this pig iron is combined with recycled scrap steel to optimize both temperature control and resource efficiency. The mixture is then fed into one of 3 LD Linz-Donawitz converters located at the site. The LD converter process involves blowing pure oxygen into the molten metal through both bottom tuyères and a top-mounted oxygen lance. This intense oxidation reaction removes impurities such as carbon, silicon, manganese, and phosphorus by converting them into gaseous compounds or slag. Known as the blowing process, it is crucial for refining pig iron into high-quality crude steel. Temperatures during blowing can rise above 3,000 degrees Celsius. To moderate this and maintain process control, scrap metal is added as a cooling agent. By the end of the cycle, the steel reaches a temperature of approximately 1,700 degrees Celsius, ideal for further processing. Each converter can handle up to 200 tons per batch, and with 3 converters in operation, Salzgitter can produce up to 12,500 tons of crude steel per day. This facility plays a vital role in meeting the global demand for high-performance steel. Vacuum ladle alloying (VPL) is a secondary metallurgical process used to fine-tune the composition and quality of crude steel. In this process, the molten steel is treated in a vacuum chamber where gases like hydrogen, nitrogen, and oxygen are removed. Alloying elements such as manganese, nickel, chromium, and molybdenum are added, ensuring precise chemical properties for specific customer or application requirements. Continuous casting plants are essential for transforming molten steel into solid semi-finished products, such as slabs or blooms. In this process, liquid steel from the ladle is poured into a tundish and then fed into a water-cooled copper mold. As the steel solidifies, it forms a strand with a thin outer shell while the interior remains molten. The strand is continuously withdrawn, cut into transportable slabs, and prepared for further rolling processes. The hot rolling mill is a key facility in steel production where semi-finished products, such as slabs from the continuous casting plant, are reheated and transformed into flat steel products. At Salzgitter Flachstahl, the slabs are first heated to approximately 1,250 degrees Celsius in large reheating furnaces to make them malleable. Once heated, the slabs pass through the reversing roughing mill, where they are progressively reduced in thickness and elongated. Next, the material moves to the finishing mill, where it undergoes several rolling stages to achieve the desired final dimensions. The result is a long, thin strip of steel known as hot-rolled coil or strip, which can reach lengths of up to 2,000 meters. Hot rolling at high temperatures reduces the strength of the material, making it easier to shape. The process also improves the grain structure and surface finish, preparing the steel for further processing or end use in various industries. The hot strip plate line cuts hot-rolled coil into flat steel plates up to 16 millimeters thick. These plates are used in sectors like machinery, construction, and special vehicle manufacturing. The pickling line removes scale and impurities from hot-rolled steel surfaces using acid baths. This process ensures a clean, smooth surface, improving steel quality and preparing it for further processing like cold rolling or coating. The cold rolling mill processes pickled hot-rolled steel strips by rolling them at room temperature to reduce thickness and improve surface quality. This enhances mechanical properties such as strength and hardness while achieving precise dimensional tolerances. At Salzgitter, the tandem cold rolling mill can produce steel sheets ranging from 0.35 to 3.0 millimeters thickness with high speed and accuracy. Cold rolling also prepares the steel for further finishing like coating or embossing. The skin pass mill, also called the temper mill, applies a light final rolling to cold rolled steel. This improves surface finish, enhances flatness, and adjusts mechanical properties like strength and flexibility for better formability. Electrolytic galvanizing is a process where cold-rolled steel sheets are coated with a thin, uniform layer of zinc in an electrolytic bath. Using an electric current, zinc ions are deposited onto the steel surface, filling pores and imperfections. This creates a smooth, corrosion-resistant coating essential for automotive and appliance industries, ensuring durability and excellent paint adhesion. Hot dip galvanizing involves immersing steel sheets in a bath of molten zinc, heated to around 450 degrees Celsius. This process forms a strong, durable zinc coating that bonds metallurgically with the steel, providing excellent corrosion resistance. At Salzgitter Flachstahl, continuous steel strips are galvanized this way, ensuring uniform protection for applications in construction, automotive, and appliance industries. Coil coating is a continuous process where galvanized steel coils are coated with organic materials like paints or plastics. This enhances corrosion resistance, appearance, and durability, tailored to customer specifications for use in construction, appliances, and automotive industries. The Fractum Model 100 is a highly efficient and innovative solution for desculling slag pots, offering a modern alternative to traditional, costly methods like drop-ball operations. This high-energy impact hammer is specifically engineered to tackle the harsh demands of breaking red-hot skulls, the solidified slag and metal residues that form within slag pots during steelmaking or foundry processes. One of the major advantages of the Fractum Model 100 is its ability to eliminate the need for a drop ball, a traditional method that relies on gravity and repetitive high-impact drops from cranes. Drop ball operations are not only time-consuming and dangerous, but also extremely costly due to equipment wear, crane fatigue, and limited control over impact precision. In contrast, the Fractum Model 100 provides a controlled, efficient, and safe impact force that breaks down even the toughest materials, including red-hot skulls, without damaging the pot or surrounding infrastructure. With the Fractum system, desculling is significantly streamlined. The hammer delivers precise, high-energy blows directly to the hardened slag mass, fracturing it efficiently while maintaining the integrity of the slag pot. This reduces downtime, improves safety for operators, and lowers maintenance costs on cranes and associated equipment. Additionally, the reduced handling time means slag pots can be turned around more quickly, increasing productivity in the plant. Breaking red-hot skulls while they're still in the pot also improves process efficiency. Since the Fractum Model 100 can handle high temperatures and maintain performance in extreme conditions, it allows operations to proceed without waiting for the material to cool, saving both time and energy. The Baiyin daylight slag tipping event of 2005 is a lesser-known but visually striking example of industrial waste disposal in China, captured famously in photographs that highlight both the scale and drama of modern industry. Located in Baiyin, Gansu Province, a city known for its extensive mining and metallurgical operations, this event showcases the dramatic process of slag tipping in broad daylight, a rare occurrence typically conducted at night due to the hazards and visual intensity involved. Slag tipping refers to the dumping of molten waste materials, or slag, which are byproducts from smelting metal ores, particularly copper in the case of Baiyin. The process involves pouring glowing molten slag from specially designed ladles or containers into slag heaps or pits. When this is done during daylight hours, the bright, lava-like streams of molten rock create an intense and surreal contrast against the industrial backdrop, giving the scene an almost apocalyptic appearance. In 2005, Baiyin's metallurgical complex was still active, despite the city's mining decline since the 1980s. The event was documented as part of broader efforts to illustrate the environmental and aesthetic impact of heavy industry in China's interior. The photographs and reports from this period captured not only the power and danger of the slag tipping process, but also the harsh working conditions faced by laborers and the environmental degradation surrounding industrial towns like Baiyin. Baiyin itself had long been a center of copper production, with operations dating back to the 1950s. At its peak, it was known as one of China's key resource cities. However, as ore resources dwindled and pollution worsened, the region began facing economic and ecological challenges. The 2005 slag tipping event, while not a disaster, became emblematic of the industrial legacy that cities like Baiyin must contend with. The balance between economic development, environmental sustainability, and worker safety.